Hello, everyone. Welcome to our Latin American webinar on physics, number 152. We are very happy today with our guest, Dr. Wren Suess, who is right now a Hubble Fellow at Stanford University. She will join us today with a very amazing seminar on the recent developments on the JWST and how this has opened a new era for distant galaxies. Dr. Suess got her BA in physics at the University of Colorado in Boulder. After that, she moved to University of California at Berkeley, where she got her PhD. And then she was a Stanford Santa Cruz Fellow at Stanford University at Santa Cruz, University of Santa California at Santa Cruz. And then now she has the prestigious fellowship, the Hubble Fellowship at Stanford. But in a year, she will join the faculty of CU Boulder as an assistant professor. Thank you very much for accepting our invitation, Wren. For everyone watching on YouTube, remember that you can ask live your questions on the chat of the YouTube channel, or you can also send us a tweet on the former Twitter. And make sure that you post your questions. We will be happy to read those questions for the speaker at the end of the presentation. And make sure that you subscribe to our YouTube channel, in our Twitter account and Facebook account, so that you are posted on the upcoming events that we are organizing for you all. Thanks again, Wren, and you can start your presentation and take it away.
Awesome. Thank you so much for the introduction, and thank you for having me. It's really exciting today to get to talk about some new results from the new James Webb Space Telescope. So I'm an observer. So I study the formation and evolution of galaxies across cosmic time. And I wanted to start just by saying a little bit about why I care so much about distant galaxies. So humans have been looking at galaxies in the night sky for a very long time. This is an example. This is actually a photographic plate of our nearest neighbor galaxy, Andromeda, that was taken from the Mount Wilson Observatory back in the 1920s, so 100 years ago. And the really cool thing about galaxies is that they represent many different things. First of all, galaxies are basically the light that lights up the dark universe. So galaxies tend to live at the centers of dark matter halos, and you can use the position of galaxies in the night sky to actually trace out some of the largest scale structures in the universe and do this kind of fundamental cosmological measurements. But galaxies are also really interesting in their own right, because they reflect this really complex interplay of a ton of different things acting on a ton of different both spatial and time scales. So galaxies are made up of stars, multi-phase gas, dark matter. They often have supermassive black holes at their centers. And all of these things, you kind of have to understand all of them if you want to really model and understand the light from distant galaxies. And so there's a really wide range of physical processes that you have to be able to model and understand, and we can never get it quite right. So we're always trying to decide what is the most important physics really driving the evolution of a given galaxy at any point in time. My other kind of favorite thing about studying galaxies is that we can actually watch galaxy formation in action. And this is because looking far away is the same thing, basically, as looking back in time, because it takes light some amount of time to get from point A to point B. And so if you are standing, looking with your little telescope at this Andromeda galaxy, it's something like 2.5 million light years away. And so it's taken that light from Andromeda about 2.5 million years to get to us here on Earth. And so we're seeing Andromeda as it was something like 2.5 million years in the past. But again, Andromeda is our closest neighbor. And so if we go look at galaxies that are further and further away, we're actually seeing them as they were further and further back in the past. And so as a very extreme example, this is actually the most distant galaxy that has ever been confirmed by humans from the James Webb Space Telescope. And this tiny little red blob is spectroscopically confirmed to lie about 13.1 billion light years away. So it's 13.1 billion. We're seeing it as it was 13.1 billion years ago. And so that's really exciting to be able to watch galaxy formation across these billion-year-long timescales. The other thing that you can tell is that this little blob here that's very distant is very red. And that's because as this light is traveling from these distant galaxies to us, the universe is actually expanding, and it's making the wavelength of those photons that are the light that we're seeing longer. And so that corresponds to this light being redder and redder as we're looking at these more and more distant objects. And so to look further in the past, we have to be able to observe this redder light. And so this is why this is the coolest thing to me, is that effectively we have a time machine just looking out at the night sky. Because all we have to do if we want to study how galaxies are forming across these billions of years is to look further and further away. And that corresponds to looking further back in time. But it is a time machine with a little bit of an asterisk, where that asterisk is that the further back that we want to look, the redder the light that we have to observe. And so this is one of the main reasons that astronomers were so excited about this new space telescope, is because we really want to be able to see into this redder part of the electromagnetic spectrum. So this is a little diagram showing going from, I guess, from the Big Bang at the very beginning of cosmic history through all of these different epochs, the formation of the first stars, the formation of the first galaxies, and then the formation of modern day galaxies all the way to our sort of present day. And so that directly corresponds to these wavelengths of light that you have to use to probe these different epochs of cosmic history. And so the Hubble Space Telescope, the reddest wavelength that you're able to observe is about 1.6 microns, which is in the near infrared. And so that means that Hubble just absolutely can't see the formation of the first galaxies, because the light from those galaxies is too red to be observable with Hubble. And so this is why, part of why we're so excited about this new JWST, because it can go much further into the infrared, and it can see the formation of the first galaxies and potentially even the first stars. The other reason that I was so excited about this telescope is that looking at different colors of light actually gives us different information about what's happening in the galaxy, and gives us these different probes of this, this multi-wavelength, very complicated process that's going on in these objects. So as a slightly more earthly example, here's an example of some zoo animals as seen in visible light, like what we would see if we went to the zoo. But if you look at them instead in infrared light, like what JWST is able to see, to humans, that's basically looks like a heat map of these things. And all of a sudden, you're gaining new information about what's the physics of these animals, where you can see these little dudes are emitting light. They are warm-blooded, where this guy is essentially the same color as the background because he's cold-blooded. And so it's the same thing with galaxies, where we can put together this multi-wavelength picture and start to understand different physical processes. So this is an example of the pillars of creation. This is a star-forming nebula. I think I had a poster of this when I was a kid from the Hubble Space Telescope. I'm sure I'm not the only one on this call who did. And so what you're seeing here, this is again an image from the Hubble Space Telescope in visible light. And what you're seeing is actually the formation of new stars. It's the birth of new stars inside these very dense cocoons of gas and dust. And so these are these kind of pillars that you can see, where you can't really see the young stars shining through this dust because the dust is obscuring them. If you look instead at near infrared light, this is the exact same picture, but you can see it looks very different because here these stars are able to shine through all but the densest dust. And so all of a sudden, there's all these little pinpricks of light in the background of this image that were previously obscured in the optical. And then if you go to even further wavelengths, the sort of furthest wavelengths that you're able to observe with something like JWST, this is the far infrared. This is a very blurry picture because this was actually the highest resolution that we had of this type of light before the launch of JWST. This is the far infrared, and we're actually seeing the dust itself glow. And so you can study the physics of this dust and start to do really complicated, actually like astrochemistry about what are these grains made of, what are the grain size distributions, what's the physics of their formation and destruction. And so ideally, you want to put together this full multi-wavelength picture in order to really understand these different parts of galaxies and be able to get an unbiased view of them. Yeah, so basically, for most galaxies over most of cosmic history, the Hubble Space Telescope was really just tracing this visible light. And so we're really not getting a full picture of what's happening in distant galaxies. So you can imagine if we had a galaxy where you're only seeing this type of visible light, if you tried to do something as simple as like how many stars are in this picture, you would get the wrong answer because you're not able to see through the dust and actually count up the total number of stars here. So, we knew about these sort of reasons that we would want to see into the infrared for a very long time. And so planning for what was then called the Next Generation Space Telescope actually started in 1989 before Hubble was even launched. This is one of the original drawings from that very long design process. And so JWST actually turns out to be the most expensive and complex observatory that humans have ever built. It started being built in 2002 and didn't finish until 2020. And so a lot of the reasons that this thing was so expensive and so complicated and took so long is because we were doing a lot of really novel engineering. And so the mirror, this is a picture with a human for scale of the primary mirror of this telescope, is composed of these 18 different segments that kind of have to perfectly align into this amazing giant hexagon. You can see this mirror is huge compared to people, and we have to launch that all into space. It's gold-plated beryllium, so you can see it's nice and shiny. It also, because we're trying to observe these very faint infrared signals, the sun, luckily for us here on Earth, is very bright in the infrared. It gives us lots of heat that we like here on the planet, but also we don't want that to bias the measurements that we're getting from our telescope. And so the telescope actually has a tennis court sized sun shield that basically puts it perennially in the shadow of the sun. And this is, again, like an insane feat of engineering. It's composed of many layers that if you look at a picture kind of look like space heat blankets. They're very thin layers that had to unfold. And so, yeah, you can't launch a tennis court into space on any kind of satellite that we have right now. And so this thing had to actually unfold once it was already outside of the Earth's atmosphere. And so it had 139 actuators and 8 different motors that had to all perfectly deploy in order to unfold this thing. And as if all of that wasn't hard enough, it's also 1 million miles away. Again, this is mostly to keep it from the heat of the Earth that would make a very strong infrared light source. So JWST was finally launched actually on Christmas Day of 2021. And this is a picture of the launch. And this is the very last video that we actually have of this thing, as this is basically the telescope detaching from the rocket. And this launch went just absolutely phenomenally well, in the sense that so this thing is 1 million miles away, and you have to have some amount of fuel to like point where you want to look in the night sky. And so for a long time, we thought that this mission would probably be limited by the amount of fuel that we could send with it. And a lot of that was trying to get it to this place that it's supposed to be orbiting, the second Lagrange point in the Earth-Moon-Sun system. But actually, Arianespace, who contributed the launch part, this is the ESA contribution, the European Space Agency contribution to this mission, they actually got the launch so perfectly well that they had to use much less fuel than they anticipated to get this thing to its final orbit. And so it all of a sudden went from what we thought would maybe last 5 years to something that we now think is going to last 10 or 20 or even more years. So that's extremely exciting that the launch went so well. You can see here, this is one of the solar panels that's unfolding from this. And so after this telescope was launched into space and everything was going well, this was still not the end of this journey. So this is the unfolding sequence. It takes about a month for this thing to actually unfold and get to its final orbit at, again, the second Lagrange point. And so this was a period where basically every astronomer, I think, was like glued to the NASA website, like refreshing for all of the updates that they were giving on all of these different things that had to happen perfectly. So like, did the sun shield actually unfold the way it was supposed to? All of this. And it was actually very, very nerve-wracking because, as you can see, like here, this is the secondary mirror of the telescope. That's one of the last things actually that was going to unfold. And so we wouldn't get data at all unless this actually happened. And so luckily everything went exactly to plan. All like 137 actuators and 8 motors or whatever, all of those things worked perfectly. And so the telescope actually deployed, which is amazing. And so again, this is a lot of why this took so long for this thing to actually happen. The launch was delayed many times, and it was because we had to be absolutely sure that this was going to work as expected. And after basically it got to its orbit, there was then 6 months of what we call commissioning. And so this is the process where we actually are aligning all of the mirrors and testing all of the different instruments. So there are actually 4 different instruments on board JWST, and all of them have to be tested in all of their different modes to make sure that the observatory is ready for general use. And so this is a picture from the WISE satellite, which was one of our previous best views of these wavelengths of light, these sort of 3 to 4 micron ranges. And this is a picture of a star. That's what this big blurry thing is. And as I play this is a GIF that will fade to the very first image that most people ever saw from JWST out of this commissioning process, which is just an image of this same star. And like, I think I could watch this video just on loop for like days because it's so amazing. So you can see this star resolve down into this tiny, tiny little point source with these big diffraction spikes. So those are hexagons, sort of in part because the primary mirror of the telescope is a hexagon. But you can also see like all of these things in the background. Those are the galaxies. So those are the things I really care about. And you can see that there's just these huge blurs that resolve down into like these really tiny sources where you're actually able to study the structure of these distant galaxies in the infrared in a way that's just like was completely impossible with previous instrumentation. And then also you can see in the JW image, all of these like faint sources that are popping up above the noise. And so this is really, really groundbreaking. This is really opening up this entire part of the electromagnetic spectrum that we weren't able to observe in this way before. And so with that, I want to talk about a couple early science results. So, we've only really had data from this telescope now for like a year and a couple months. So a lot of stuff is still changing, and we're really still trying to piece together, a picture of just everything that has changed. So everything I tell you from this point is sort of like still a little bit up for debate. We're starting to find some really interesting things, but I think it's probably going to be a few years yet before we've really settled on a new understanding of like exactly how all of our thoughts about the distant universe have really changed with all of this new data. But the first thing I wanted to talk about is the first galaxies, because as I mentioned previously, this new infrared imaging is really critical in order to let us look for the formation of the first galaxies. And in terms of timescales, this is looking for galaxies something like 300 to 400 million years after the Big Bang, which maybe sounds like a long time if you're thinking about human timescales. But in terms of cosmic history, the entire universe is 13.6 billion years old. And so this is really looking at a very, very infant young universe. And the expectation that we had before JWST is that we would probably find just a few very small faint galaxies. So this is a simulation actually of what happens if you just have a universe full of dark matter and you have a little bit of structure there, and then you let the dark matter collapse in on itself just due to the effects of gravity. And so you can see that there are these, these big sort of filamentary structures that are forming and these really dense pockets. And these sort of densest things here in dark matter, that's where you would expect to find the galaxies forming. And so if you think about these dark matter simulations, and then you think about what you might be able to observe, of course, today when we look, there's big galaxies lying at the centers of these big dark matter halos. But if you were to, wind back the clock on the universe and look at it somewhere around here, there's not that much structure yet. And these dark matter halos are not very large yet. And so you might not expect to find very many galaxies. And if you do find them, you wouldn't expect them to be particularly bright. And you would expect them to probably look quite different from galaxies in the local universe. And then the reality is that basically as soon as we turned on the telescope, like the first image that we got, we already found two very distant galaxies. And this was a really big surprise because it was, the expectation, I think, was that we would have to look for, take 6 consecutive months of data before we would get, a reasonable probability of observing one distant galaxy. And to sort of turn on the telescope and immediately start finding them was very, very surprising. So since then, we've gotten more data. There have been, this is a tiny, tiny number of the papers that have been published on this topic. But this is a sort of nice collection made by Richard Bowens showing the brightness of galaxies as a function of redshift, where here redshift is just a different way of measuring time, where the now is basically redshift 0 off to the left of this plot. And the beginning of the universe is redshift, many. And so redshift 18 is very, very far in the past. This is only a couple 100 million years after the Big Bang. And so all of these gray points are galaxies that were found by the Hubble Space Telescope, where again, you're really not able to probe these earliest epochs of cosmic history. And then these points here are galaxies that were found just after the first 6 or 8 months of JWST observations. And there's a ton of them. So this is really starting to kind of bring up this question of are we actually seeing too many of these early galaxies compared to what we would expect? And this is a different way of looking at this. This is the expected number of these early galaxies as a function of how bright they are. And all of these curves here are predictions from different theoretical models. And if you put the kind of number that we've already observed on here, it lies up here, which is higher than basically all of the models. It sort of goes through this one point, which was a much older model that wasn't fully calibrated to all of the recent HST data. And so it seems like the observations that we're seeing are potentially in tension with these different models for how galaxies are forming. And it seems like we're seeing too many of these very bright galaxies very early in the universe. And so some of these, there's a lot of modeling that goes into trying to understand how far away a galaxy is. So some of these galaxies might turn out to be a little bit closer than we think they are. We need a different type of observations. So instead of looking at imaging, we need to look at spectroscopy to really pin down the redshifts. But many of these galaxies, this is actually an underestimate. There are more observations since I made this slide. It's something like a dozen of these galaxies now have been spectroscopically confirmed to lie in the very, very distant universe. And so I think it's quite, we don't know quite what this means yet, but I think it's a very solid thing at this point to say that galaxies really did begin forming something like 200 million years after the Big Bang, which many people think is unexpected, especially compared to what we thought we would see before the telescope was launched. And so it's unclear yet what this exactly means. So one possibility is that there's something odd about these early galaxies. So maybe they are brighter than expected because of something, physically different about them. So we're seeing strong line emission for some reason that we didn't expect. or it's sort of a sample selection effect, and we're seeing preferentially bright ones for reasons of the survey areas that we've looked at or something like that. Or some people have said that this might be evidence of tension with our lambda CDM model of cosmology. I think that's a little bit of a step too far, because we have a lot of really good constraints on our cosmological model from a lot of things that are much less complicated than the astrophysics of galaxies that we've seen for less than a year. But this is sort of a very active ongoing area of research to try and understand these early galaxies and understand why they seem to be so bright so early. I also wanted to highlight a couple other interesting sort of science cases. So I told you before about how dust obscures some of the light from distant galaxies by showing you these sort of pillars of creation. And I want to show you an example of some galaxies that actually were completely invisible to HST that are much closer by. So this is an image from the Hubble Space Telescope. This is a very, very deep integration. You can see here there's a couple galaxies. And this will again flip back and forth to a JWST image, where all of a sudden there's this giant red blob that appeared out of nowhere. So this is much closer by than those galaxies that I was talking about before. This is at about redshift 2 or 3. So only a few billion years ago, not more than 10 billion years ago. But we just didn't see this thing at all. And that's because it's very dusty. And so actually all of the light from this galaxy was obscured by dust and not visible in the optical parts of the spectrum that we were able to see with HST. And so there's, a whole population of these things. They all look super weird. Here are a few examples. They're often very clumpy or elongated. And again, all of these things were completely invisible before to the Hubble Space Telescope. And so this is really the first time that we've been able to really look at these galaxies in detail. And in particular, it's the first time that we've been able to study their structures, because we were able to see some very bright galaxies in the infrared before with things like WISE and Spitzer, but the beam size of the telescope is bigger than these cutouts that I've made. And so we weren't able to actually resolve them and see if they're disk galaxies, if they're irregular, if they're clumpy, what's happening with their morphologies. So this is a very exciting avenue of ongoing research. And then I want to tell you about one other class of sort of previously invisible things that I'm particularly excited about. So one of the things that I was doing relatively recently was to look at these, we thought, very well-studied galaxies, again, relatively close by at redshift 1 to 3. This is a period in cosmic history that we call cosmic noon, because it's actually the peak of the star formation density of the entire universe. So this is basically the most exciting time in the universe in some ways. It's the peak of star formation. It's when we start to see the emergence of this population of quenched galaxies, so galaxies that are no longer forming stars, which is most of the galaxies that we see around us today. And so I was looking at these galaxies with the idea of trying to measure their sizes in this new JWST imaging and see if their sizes are different as a function of wavelength. And then I just started looking at cutouts of these galaxies. And so these are cutouts from the Hubble Space Telescope, where you can see these are 3 examples of 3 galaxies. They look pretty boring. They're just like ellipses. And then I was looking actually at the same wavelength of light. So not even going to redder wavelengths, but the same wavelength of light with JWST. And the big difference here is actually the resolution of the telescope. So because JWST has this giant mirror, it actually has about 3 times the resolution of HST, even at fixed wavelength. And so you can see, hopefully this is coming across well in the slides, but there are all these little dots that you couldn't see before in these HST imaging. And this is some of the deepest imaging that we have with HST. And these little dots are just completely invisible. And so if you actually model all of these little things, here I'm circling all of those little dots if they're at the same redshift as this thing in the middle that I've subtracted out here. And many of these are at the same redshift. And so what this means actually is that these are satellite galaxies. that we're seeing now when the universe was billions of years old. So this is really exciting because we've never really been able to look at these satellite galaxies so far away. And so this is something that's, it's very clear that we should be able to see. The Milky Way itself, our own galaxy, is surrounded by a ton of satellites that we're actually still in the process of discovering because they're so faint compared to the primary galaxy. But we've never been able to see them this far away in the past. And so this is one way of looking at this. So this is the ratio of basically how big the primary galaxy is compared to how big its companion galaxies are as a function of how far away they are. And this is where we were able to observe with HST. So we were able to see things that were up to about 10 times fainter than their host. And so in terms of the Milky Way, this is basically the same mass as the LMC, the Large Magellanic Cloud, which is the most massive companion that the Milky Way has. And all of a sudden with JWST, we're able to see all of these faint satellites that are up to 10,000 times fainter than their primary host. And so I think this is really exciting because it's again opening up a whole sort of new field where we get to study the demographics of these satellite galaxies as they're just falling into their hosts, probably for the first time. And again, we're now able to do this not just for our sort of local system, but we're able to do it when the universe was less than half of its current age, which is very cool. So I wanted to conclude just by talking about a few things that I'm excited about upcoming. Again, this is a very, very new telescope. And so we're really still figuring out a lot of the things that we can do with it. And so I'm really excited to, again, study this detailed physics of these very early galaxies and try and actually understand what's going on in them. We might potentially see the formation of some of the first stars. Nobody has found a good candidate for a very, very early star yet, but we are still looking. Part of the problem is we don't quite know what we're looking for. We don't know what stars should look like if they form right after the Big Bang, so it's hard to predict some of the observational signatures. I'm excited to get a full census of star formation across cosmic time, and so to really include all of these dust-obscured populations and see how they contribute to this sort of cosmic star formation rate density. And then again, I want to understand the detailed structures of some of these more local galaxies that we're able to resolve for the very first time with this amazing instrument and start to ask questions about how these things are growing and changing over time. And so one of the surveys I'm really excited about is called Uncover. So this is a JWST image of this field. You can see here there's a very bright star. There's all of these sort of white galaxies in this 3-color image. This is actually a cluster, a galaxy cluster that's at about redshift 0.5. And the really cool thing is that this cluster is lensing these background galaxies and actually magnifying all of these galaxies that are in the background of this image. Uncover is an amazing collaboration. It's led by Eva Labe and Rachel Pazanson. To show you sort of a zoom in around the cluster, you can see the effect of this lens. It's really like just holding a magnifying lens to the very distant universe, where you can see these galaxies here that are in these big arcs. And so those are very distant galaxies that are being magnified to many times the brightness and the spatial resolution that you would expect by this cluster. And so this is a really great way to get a detailed view at the spatially resolved structures of very faint galaxies in the very early universe. And so we're already doing a lot of very exciting science with Uncover. We have spectra of a bunch of these galaxies. We've identified a lot of early galaxies, a lot of weird things that are closer by. But I wanted to briefly mention something that I'm really excited about, which is to add on to this data set. So this is the filter coverage possible with the NearCam instrument on JWST, where basically each one of these filters, these little curves, this is one way of looking at the distant universe in a different wavelength. And it's averaging over this whole sort of wavelength range that's in this filter curve. And so all the observations I've shown you basically are actually from these so-called broadband filters, where you're averaging over a huge chunk of wavelength space and then making a picture basically of that whole chunk of wavelength space. But I think one of the most innovative things on NIRCam is that actually we've never had medium band filters in space really in this way. But NIRCam has a dozen of these medium band filters where you can see every one of these broadband filters has like something between 2 and 4 of these medium band filters sitting inside of it. And these medium band filters are really good for like showing us the detailed physics of these distant galaxies, because there's a lot less uncertainty about where exactly in wavelength you're looking, because you're looking at this really small chunk of wavelength space. And so if you see, you know, a really big emission in one of these medium band filters, you know that there's a very strong emission line in one of these filters or something like this. And so this gives us a really detailed view of the astrophysics of distant galaxies. And actually in 21 days, our observing window opens for the program that I'm leading for JWST cycle 3, which is basically to observe all dozen of these medium band filters on that same uncover field that I just showed you. And so we estimate that this adding in all this additional data is going to improve our estimates of the stellar masses and redshifts and all these physical properties of these galaxies by a factor of about 3. And we're going to be able to make emission line maps to really study these star forming regions in detail. And so this is what this looks like. This is public data from a medium band survey that was just looking at two medium band filters, where here the green in this RGB image is showing the medium band emission. And you can see here there are these like little clumps that are really green, or this sort of strange extended structure or whatever this shape is here. And so that's actually strong line emission, and it's tracing out the star forming regions in these galaxies. And so we're able to do these really cool spatially resolved studies in a way that wasn't really possible before. And it's also not really possible with the existing sort of broadband data. And so we're going to do this for a huge number of galaxies across, you know, a large number of emission lines and a large redshift range. These are just a few examples of some of the galaxies. There's about 50,000 galaxies that we'll be looking at. But these are, you know, a dozen of them where there's this is like, I think this is called the firework galaxy, where it's got this really weird, strange structure. There are these big lensed arcs that will be able to get sort of 100 parsec resolution of these galaxies at, you know, redshift 8, which is just very, very crazy, not possible without the help of this gravitational lensing. And so with that, I want to just conclude by saying, you know, again, this telescope is amazing. We've only had it for a little bit of time, and there's so much left to learn about the physics of the distant universe. And it's a very exciting time to be studying galaxies. So with that, I'll take any questions that folks have.
Thank you very much, Wren, for this amazing talk. And now I'm going to open the questions for the people who are in the call, and also for everyone who is in the YouTube channel. Please ask your questions in the chat, and we'll read the questions for Wren. So while you do that, I'm going to ask if maybe Roberto or Alejandro have any questions.
Thank you, Wren. It was an amazing talk. I have several questions, and I find this fascinating. So I have one question, which is more, when we do this spectroscopically confirmed distances, do we have a sense of the error bar? What is like the biggest source is coming from, in the sense, is it systematic or if it's instrumental? And related, and maybe you can answer this one, is like, and the procedure to measure redshift is the same one across distances? And if so, how can we trust that procedure?
Totally. So that's a great question. So there's 2 ways of getting the distance to something. I'm actually going to stop screen sharing for a second, because I think I have a better slide, if I can find it. So basically there's, it's in a different presentation. Okay, so there's like 2 ways of trying to understand how far away things are. And this is fundamentally because we have these very complicated models of distant galaxies. And so as an example, here I'll share this other presentation. So this is an example of what this data looks like here in this little plot. So this is the flux density. So this is basically how bright things are as a function of wavelength. And this is a model of an example galaxy. It's very complicated. These models have, if you want to, like 100+ free parameters that you can actually turn the knobs on. And so there's two ways to get information about the distance of a galaxy, because essentially what you're trying to see is like the shift in the x-axis of where this thing is. So the first option is to get just these data points here from imaging, and then to fit a very complicated model. And so that is what we've done for a lot of these measurements of distant galaxies, is to fit this photometric data. And there we are absolutely definitively systematics dominated. No way around that, because basically there's a lot of degenerate solutions to these complicated models. And so the reason that we need spectra is because spectra actually give us information on the line emission from these galaxies. And so you're actually pinpointing a specific spectral line to a specific part of wavelength space. So you can see here this black, this is spectroscopic data. And the measurement that's being made here for these very, very distant galaxies is this break here. This is called the Lyman break. This is basically blue word of this. There's no emission from galaxies because it's all absorbed by the intergalactic medium. And so these are what the spectroscopic conformation looks like. You can't make this any other way than having these very distant galaxies. There's no way to confuse this Lyman break for anything else. But for other galaxies, we're actually sometimes seeing actually emission lines. So there's very distinctive patterns of emission lines from different elements that you're able to pinpoint. And so this is more dominated. This has very, very small error bars on it. Yeah. Long answer, but.
Thank you. I have more questions, but I don't know, Walter, you.
Right, Roberto, do you have a question?
Yes, I have a question. Very, very, very nice the webinar. Right?
Thank you.
Yeah, I was wondering how the James Webb will because of this lambda CDM controversy with the Hubble tension. Is it possible to measure and try to give an answer to this tension between the very early universe tension?
Yeah. That's a good question. So just to explain a little bit more about the question. So basically right now, one of the most fundamental cosmological measurements that we can make is this Hubble constant. And right now there's a, what is it, 6.5, 5.5 something sigma tension between the measurements that we're able to make from the cosmic microwave background and the measurements that we're able to make from very local supernovae. And so I think it's very hard to constrain that with galaxies because galaxies are too complicated. But the measurement that I have seen that I am more excited about for JWST is actually looking at lensed supernovae. And so the way that this measurement works is that you have to have very high resolution imaging, which is great with JWST. You can potentially find some of these things. Where there's a supernova that goes off that's lensed by a galaxy, the same way I showed you this cluster was lensing this light. And you can look at the different images of the supernova and you can basically calculate a time delay, and that can give you the Hubble constant. And so I think there's been at least one paper doing this with JWST, and that puts, it's not yet competitive with the sort of local supernova measurements, but it's not that far off from the fact that there's like one or two of these that have ever been observed. And so JWST will potentially find some of these. And then actually the next successor, which is the Nancy Grace Roman Space Telescope, which is an optical telescope that has a very, very wide field of view, is expected to find many, many more. So I think that's probably a better route forwards. But we are still trying to figure out why these early galaxies happen. And in particular, like they just seem very bright and very massive. And so I think there's a way to explain it without breaking lambda CDM, but we don't know what it is yet.
Thanks. And another question, just very fast, about this very weird early galaxies.
Mm-hmm.
Any information about if also its composition is weird in some way?
Yeah.
Not only hydrogen, I mean, with the with the light elements, abundancy or
Totally.
something like that?
Yeah, so people have just sort of started looking into this. So there are a lot of papers that I haven't read in enough detail necessarily to maybe summarize. But some of the things that people are really interested in measuring are the metal abundance of some of these galaxies. So that sort of tells you in these very early galaxies how many generations of star formation that they've had in order to be enriched. And I don't think there's anything too crazy that has come out of the total metallicity. But there are some really weird ratios of emission lines that people are finding in some of these distant galaxies. And what that tells you is that you probably have, these galaxies probably have star formation conditions that are very different than the local universe. And in particular, it seems like they have very low total metal content, but they have a lot of these, we call them alpha elements. It's things like carbon and oxygen that come from type 2 supernovae, so core collapse supernovae. And so they're very enhanced in these alpha elements, which makes sense because they haven't had time for these type 1A supernova to go off yet. So things that make iron. But it does mean that we don't have models yet for those types of stellar populations. And so it's actually very hard to fit some of the detailed physics of these galaxies. Some of them also have very large supermassive black holes. As indicated from having these really broad wings on the emission features that are indicating very high velocity gas. And so there's also people that have been looking specifically at the supermassive black holes in some of these early galaxies and trying to compare those with predictions where you can start to compare to like what we think the so-called like seed masses are for black holes. So like how big a thing do you have to start with in order for it to grow into a supermassive black hole? So we're starting to probe that regime, but I think we need more spectra. Yeah.
Okay, cool.
Thank you. Before giving a chance to Alejandro to ask his other questions, we have a question from YouTube. Hugo Vicente is asking, what about AGN activity of these far galaxies? Is there any data?
Oh, yeah. So I guess I sort of just answered that a little bit. So we are seeing a lot of these active galactic nuclei, these supermassive black holes in some of these early galaxies. In particular, there are some that are different than we thought that they would look like. So I'll see, I maybe have a slide if I pull one of these up, but there is a very early paper that I was part of trying to figure out if we had very massive galaxies in the distant universe. Yeah, I don't have the slide offhand. But basically it turned out that the solution to this galaxy that we thought was a very distant galaxy that was very massive is that it was actually a much closer by black hole. And the reason that we didn't realize that at first is because it's a very odd looking one. And so people have started referring to this population mostly as little red dots because they're very, very little and very red. And so it's a very different type of supermassive black hole where we think they're very obscured by dust, which is why they're red, but they also have some contribution from scattered light that's like leaking out that hasn't been affected by the dust. So they have this very different spectrum than what we've really seen before, where they're essentially very red in the red and either flat or very blue in the blue, where normally you would expect just a spectrum that looks like this, we're instead seeing sort of this. And so that's been very unexpected. And it seems like a lot of these very reddened AGN, this is a population that we don't really see in the local universe. So it seems like by looking at higher redshift, we're seeing more of these reddened AGN and more of these sort of like leaking red AGN.
Thank you. Alejandro?
Thank you. So you partially answered one of my questions, but then maybe the last one, a quick one, is like, if we want to see like that far away in some sense, we are also at the limit of this new instrument, right? Mm-hmm. So when we do that, I mean, one thing is maybe to see it and the other one is to resolve it. So I would just like to hear your thoughts about like the precision or the precise astrophysical measurement you can make for this far distance, because maybe you are just seeing them, and then how precise is it and how we do it?
Yeah, totally. So, I mean, so to show you again, I guess this, the image of this most distant thing that we've spectroscopically confirmed. It's that itty bitty little red blob. So this one is very marginally spatially resolved. But many of them are essentially point sources. So we can't tell whether or not they're an infinitesimally tiny point or something that is quite significantly bigger than that. And so a few of these distant galaxies, we are able to actually see that they're spread out over some area. This is really hard to do because it requires really precise modeling of the point spread function of the telescope, which is something that you need to really calibrate very well. And I worry that we haven't done it at quite this precision yet. I think in terms of sort of this really affects the interpretation of some of these distant objects, because if it is a supermassive black hole, it has to be a point source. Because, you know, mathematically, like black holes are way too tiny to actually resolve. And so I think there's one galaxy in particular, it's the most distant found object with the Hubble Space Telescope. It's called GNZ11. It looks like a point source to JWST. And so there's been this actually huge debate in the literature of like, is it a galaxy that's just unresolved, or is it a point source because it's only a supermassive black hole? And so like, ideally, we would have a telescope that's like 3 times bigger than this, and we would be able to get better resolution. That is a very distant proposition, I think. So for now, we're doing what we can with the spatial resolution that we have. And again, JWST is like, gosh, I don't know, like at least 10 times better resolution than Spitzer, which was sort of our previous view of this. And so we're doing a lot better. Obviously, we would like a future telescope, but JWST took so long and was so expensive that I worry it might be a while before we convince people to give us one. Yeah.
Thank you.
Thanks. And so finally, when you mentioned that when looking at these distant galaxies, you started seeing some invisible galaxies or galaxies that you couldn't see.
Yeah.
So I guess this can connect easily with what some people call a puzzle. Some people say that there is no puzzle with the missing satellites problem in small scale structure that sometimes people point as having controversy with the standard lambda CDM.
Yeah.
But then will the presence of this or the access that the JWST give us to these satellites in other galaxies help to sort of settle the debate about if that is a problem or not in cosmology?
Yeah, that's a great question. So the missing satellites problem is mostly like in the Milky Way and very local things. And so I think JWST is probably not going to help that much with our local system, just because we have such precise measurements of the local universe from other missions. I think part of it seems like the missing satellites problem to me is like maybe including baryonic physics can change the number of satellites that you get. But the really interesting thing I think about the satellites is, you know, with this thing I was showing is really about looking at the redshift evolution of how many satellites a galaxy has. This is something that actually, like, before I got on this call, I'm writing a proposal to do to try and make those measurements and to really compare them to different cosmological models. So we're going to look at different models and then predict what they say the satellite mass function should be at redshift 0, which is going to be right because everybody's calibrated their models to match it. But it's not clear that the models definitely make different predictions at redshift 1 or redshift 2. And so we're now finally able to get those measurements from JWST and start to actually probe that. I don't know if it will fix the missing satellite problem, but I think it will tell us something about the connection between galaxies and their halos. So like, when do you actually see a galaxy form in a dark matter halo? And what's the kind of occupation fraction of those? And some of those predictions are very different at redshift 1 or 2 than they are in the local universe. But we have not yet had time to make that measurement, but I would like to. So, yeah.
Excellent. All right, so I think that then this brings us to the end of this webinar. Thank you very much, Wren, again, for this amazing talk. We've learned a lot, and it's very exciting the future that the JWST is giving us. To all who are watching, remember to stay put with the next announcements for future webinars, and make sure that you subscribe through all the virtual channels so that you get our announcements. Thank you again, and I hope that you have a great year before you join your faculty position at Colorado. And we'll see you all in the next webinar.
Thanks so much.